Oh, good. Yeah, that's just Alexis who sends out reminders. Okay, never mind. Yeah, it's never. Okay.
So definitely has to start to learn space for us.
And me usually. Yeah.
Yeah, it was on a device.
Sorry?
Okay. Good morning, everyone, and welcome to the joint MEBME seminar. So this is hosted by the Department of Biomedical Engineering Department. My name is Vijay Vedula, and I'm an assistant professor in the mechanical engineering at Columbia. Today, we continue to offer this seminar in a hybrid format. So we have both virtual audience and also a live audience. So we will have our speaker will present for about 45 minutes, and we'll have about 15 minutes for Q&A. For the virtual audience throughout the presentation, we will use the Q&A feature, not the chat feature towards the bottom in the bottom of the screen. So we'll just use the Q&A. And the live audience, you can ask questions at any time during the Q&A. So we'll try to answer as many questions as possible, but we'll keep it towards the end. But in case if the question is not answered, then you can reach out to the speaker. Okay, so today we are excited to invite Professor Corinne Henak from the University of Wisconsin-Madison. So Professor Henak is affiliated with the Department of Mechanical Engineering. She's an assistant professor. She also has affiliations with the Department of Orthopedics and the Rehabilitation, and also the Department of Biomedical Engineering. So Professor Henak, she graduated with a bachelor's degree in mechanical engineering from University of Denver at Colorado in 2008. And then she did her PhD at University of Utah, Salt Lake City, working under Professor Jeff Weiss. That was in 2013. And then she did her postdoc at Cornell University. So Professor Henak their research mission is to drive fundamental knowledge generation and tool development to improve the quality of life, primarily focused on musculoskeletal biomechanics, musculoskeletal diseases applied to both humans and animals. So welcome, Corinne.
All right. Thank you for the introduction. Good morning. I'm going to see if I can get my screen shared correctly here. All right, there we go. So as Vijay said, I will be presenting on some basic science to prevent osteoarthritis. I'm going to talk about two different studies. So there'll be a little bit of two halves, but we will hold questions at the end just so the online folks have a chance as well. Before I jump into the research motivation, I do just want to mention a little bit about the University of Wisconsin-Madison and more generally my lab. So I know that sometimes from the coast, we don't think about the Midwest a ton, but University of Wisconsin-Madison is beautiful. We're a large public university on 4 lakes, so a lot of great things to do outdoors, really strong College of Engineering, vet school, med school on the same campus. So I'll just throw that plug out there that if you're looking towards grad school postdocs, keep us in mind. And then more broadly, for my lab, obviously I'll focus on a few projects, but just to give you a sense of the things that we do a lot of work on failure in orthopedic tissues. I'm very interested in understanding what causes failure of bone and of cartilage, a little bit less.
Let's just get rid of this. There's something. I feel like it's gonna get in the way of every single one of your.
Sure. Harry, are we able to move the video
I just want
on
to get
that
rid of
screen?
that little thing. And
Yeah,
yeah, but I can't. Okay. Oh, thanks.
yeah, no worries.
Good.
Good call, okay.
Was that, or at least were you talking about the video?
Yeah,
This-
no, just that, and if you want to get rid of that as well, so it's just
Move that down.
yeah. You have to make it small, I think. Maybe down there.
Sure, looks great. Yeah, that should be mostly the other way. Okay, thank you. All right, so we do a lot of failure research. We also look at evaluation of material behavior. I'll touch a little bit on that today. That's mostly in service of understanding failure. And then finally, we're interested in regeneration and repair. All right, I'll find my mouse. There we go. All right, so to start off with a little bit of background, I mean, I know this is BME, and so folks probably have some sense of osteoarthritis, but I do want to make sure we're all talking about the same tissue. So the cartilage that I am focused on today is articular cartilage or hyaline cartilage. This is the cartilage that in a mature animal lines the ends of the long bones. In healthy animals or animals with healthy joints, hyaline cartilage is one of the most beautiful things you will ever see. It's got this beautiful glassy appearance. It's smooth, it has a low coefficient of friction. The disease that we're focused on is osteoarthritis. And so an arthritic joint actually affects all of the tissues of the joint, with cartilage being one of the major players in the disease. But in an arthritic joint, the cartilage has started to fail, and also tendon and ligament and meniscus and bone undergo various changes. So why are we interested in this? Osteoarthritis is not killing people directly, but it is a pretty burdensome disease. So in the knee, we have the highest lifetime risk of osteoarthritis. That's a 1 in 2 lifetime risk of OA. Slightly lower in the hip at 1 in 4, and even lower in the ankle, where there's an estimated 8 to 10 times less osteoarthritis than in the knee. Right, so all of these numbers mean that you probably know or are somebody who has an arthritic joint. And so from there, you probably have some sense of the impact on the quality of life. Right. There's an estimated 80% of osteoarthritis patients that have limited movement. And this is where this disease starts to get at the burden. If you have limited movement, it impacts what you can do on a daily basis, and ultimately it can impact your overall health, mental and physical. When we look at the economic impacts, the 2014 cost was $626 billion for medical costs related to joint pain. And just as a number, that was 3.6% of the US GDP. So relatively large burdens, both for the individual patient who might have this loss of function and for the medical system overall. Now, as a mechanical engineer at my core, right, the question of why are we talking about a disease as mechanical engineers really comes back to this link of osteoarthritis being at some level mechanically mediated. So that's not a good sign. Let's see.
That's not
Is that-
normal, but it's fine.
You're okay? All right. Okay, so looking at these lower extremities, we know that there is some mechanical link. It's not perfect, but it's definitely there. So just as some examples, in the knee, there's about a 20% OA rate in 22 years after ACL injury. As you can see for the athlete here, people with ACL injury are often young, they're often pretty mobile. So having osteoarthritis a few decades after an injury when you're maybe in your 20s and 30s at the time of injury is not ideal. When we look at the hip, the current understanding is that subtle anatomical abnormalities cause most hip OA. These anatomical abnormalities are things like dysplasia, which is what's shown in these radiographs. So that's a shallow hip socket. And also things like femoroacetabular impingement, where there's actually some impingement between the socket and the femur. In the ankle, again, there's this traumatic injury history that can play into ankle osteoarthritis, where 13 to 22% of patients with ankle osteoarthritis have some history of a traumatic sprain. And again, in several of these joints, primarily the hip and the knee, there's an association or an increased odds ratio for occupations with heavy manual labor, so farmers and construction workers. All right, so this observation that osteoarthritis is mechanically mediated is not brand new. So what's already been done to try to tease out this link? There's been a long history of using contact mechanics, so whether that's finite element analysis to predict contact pressures and other contact mechanics in the joints, or discrete element analysis to predict these rates of osteoarthritis. There's been some really elegant work on this where if you look at populations over time, so these large databases, and you have a well-tuned model with a threshold that is specific for that database, then you can start to predict failure. And then similarly, some folks have taken this a little bit further and said, you know, we're not interested just in contact pressures because contact pressure is not probably causing failure. Why don't we look at things like stress invariance? So first and third principal stresses, shear stresses. And again, there's pretty good predictivity. So this is looking at different, what's called Kellgren-Lawrence grades. So for example, if you look at that red line, that's saying how well can this prediction distinguish between a 0, that's somebody with no OA, and a 3, that's somebody with pretty severe OA. But again, with these prior studies, a lot of the mechanistic understanding is incomplete. And so that drives us back to this idea that we need to do some more basic science in the lab to really understand what is governing failure, what are the thresholds at which cartilage fails. So where have people been with this before? There is a fair amount of work looking at impact-induced cracking. So this is mimicking the type of injury that would happen under a high rate traumatic load. Sometimes this is a drop tower, dropping weight from a height, spring-loaded impactors. This is pretty widely evaluated, but hasn't really gotten us too much at mechanism yet. Usually what these studies are able to correlate is energy put into the system to some % damage, whether that's cracking on the surface or cell death. And this kind of idea of more controlled cutting or indentation experiments have been less common. The study that I highlight on the right here does show that there's some relationship between the blade speed on the horizontal axis, so how quickly this sample is being loaded, and the force required to create a crack. However, in my opinion, this isn't quite tight enough yet for us to know exactly what's creating that damage, right? So with all of that, we're going to start on the first study looking at what can create a crack in cartilage. If we dive a little bit deeper into the cartilage structure and behavior, which of course then governs its material behavior, cartilage is mostly extracellular matrix in a mature animal. We have type 2 collagen fibers. So for those of you that are in the type 1 world, type 2 is also fiber forming. The fibers are a little bit smaller diameter than type 1. We have proteoglycans and GAGs, so we've got a negative fixed charge, and then we have chondrocytes. I'm not going to focus on the chondrocytes for this first half of the study because they have a relatively low volume in the overall tissue. They probably don't contribute meaningfully to the failure mechanics. But what does contribute is this water and proteoglycans, which creates a poroelastic relaxation in the tissue. And then viscoelasticity or solid phase viscoelasticity comes primarily from the collagen fibers. So knowing that there are these two different energy dissipation mechanisms in cartilage, we can play with those different features in order to shift how much subfailure energy is dissipated. So one of the tools that we use to do that is just putting these samples in different concentration sodium chloride. So 0.15 is going to be kind of your normal, right? That's standard osmolarity. If you shift the osmolarity to higher or lower, you can in fact shift the energy dissipation. So this over on the right shows subfailure properties where we have a frequency sweep. This was a 6 millimeter diameter cylindrical plug, frequency sweep from about 75 hertz to just above 300 hertz. And what I want you to notice here is that if you look at the lower osmolarity concentrations, so the yellow and the green lines, which have a phase angle about 5 degrees and a little bit higher, there is a dramatic shift then when you go to the higher osmolarity, which is the blue and the purple line closer to 10 degrees phase shift. All right, so phase shift is a measure of the energy dissipation via viscoelasticity. And this is just, again, a proof of concept that when we shift the osmolarity, we can in fact shift the amount of energy that's dissipated. All right, so we're looking at an energy dissipation framework and trying to understand a little bit more cleanly, how does cartilage failure occur? For all of the studies that I'll talk about today, we have been using pig patella. Pigs are our choice model because they have relatively thick cartilage, and it is relatively comparable to human cartilage, but of course we can get a more controlled population, right? They all have the same diet, they all have the same floors, all of that kind of thing. And there are also a lot of pigs in Wisconsin, so we have pretty good access to them. We pull out 6 millimeter diameter cylindrical cores, and then for our cartilage microfracture study, we looked at 4 different conditions. We had cartilage that was either intact or gag depleted, for evaluating the influence of poroelastic relaxations. And then we looked at different osmolarity solutions. So for the intact and gag depleted, that was all at our normal osmolarity. We then also took intact samples and put them in hyper or hypoosmolar conditions. We use a microindentation setup on a tabletop test machine. So you can see kind of a schematic or an image actually of what our test setup looks like. This is a small radius spheroconical indenter tip. That's actually something borrowed from like a Bruker nano indenter, but we just put that onto our tabletop test machine. It's actually 100 micron tip radius. So that's the diameter that we're working, or the radius that we're working with for all of these. And then we loaded across different loading rates to go from the extremely fast 5 millimeters per second, where we don't expect many of the subfailure relaxations to occur, to a very slow 5 microns per second. And for this, we were able to test our intact normal osmolarity across all loading rates. For a gag depleted, we couldn't actually get them to crack at the slowest loading rate. And then for our hyper and hypoosmolar, we looked at the 2 extreme rates. So we've got a few different conditions going on here. When we wanted to tie this back to relaxations, we pulled stress relaxation curves. So this is just looking at our intact and our gag depleted. And these are time versus load curves. So what you can see initially from these 2 curves is that our intact samples reached a higher peak load, and that our gag depleted relaxed a little bit more quickly. To actually analyze these data, we did reduced relaxation curves based on the peak forces and the equilibrium forces. When we looked at our data under fracture, these are representative curves for the intact and the gag depleted across our 4 different loading curves. For all of these tests, these were displacement controlled tests. So we've got displacement on the horizontal axis, force on the vertical axis, or load. And what we're identifying as our fracture point is when that load drops, right? So even qualitatively, you can start to see that there's some trends as we move to the slower loading rate. Our curves tend to go to the right in any given color. And then between the different conditions, between the pink and the cyan, you tend to have a shift where the pink is a little bit further to the right. We look at just an individual curve. We pulled out 4 different parameters for all of our microfracture studies. We pulled out the critical load, the critical displacement, the critical total work. That's the area under the load displacement curve up to failure. And that is both the combined work for fracture and also any sub-failure dissipation through viscoelastic and poroelastic mechanisms. And then we pulled out the critical time, which you can't see on this plot, but that was how long it took for that fracture event to occur if we're looking at the force time or the displacement time curve. Following that, we also looked at our crack morphology. These are just bright field images. And what you see here is one of our representative images. We take our samples, we wipe the surface with India ink so that we can see that crack a little bit more clearly. And then we measured 2 things for this. We did measure length, but the primary feature that we were focused on was number of branches. So in this case, this crack has 3 different branches. It's kind of star-shaped. We also had cracks that looked more like lines, but we would just call those two cracks or 2 branches. And then, as I said, we measured length, which was a little bit more subjective for this study. So the number of branches was our primary focus. We wanted to use some of our data at the fastest loading rates in order to estimate the fracture energy or critical energy release rate. So to do this, we built an axisymmetric FE model. We phenomenologically fit those fast loading rates to an Ogden hyperelastic constitutive model, first order. And what you see in this plot, these are load displacement curves. These are from our fracture tests, but before the fracture actually occurred. For the intact, that's that blue color, and you can see the actual experimental data in the blue with the shaded region as plus or minus 1 standard deviation, and then the black lines are the fits. And then the kind of pinkish red is our gag depleted, and in that case, again, you see the black lines as the fits. So not perfect fits, but we chose this particular model because there was an existing set of data that allowed us to fit our critical energy release rate based on mode 1 fracture toughness from a sharp punch penetration model. So reasonably close to the experimental setup that we had. All right, the other piece that we looked at was clustering these samples into different failure regimes. We took our experimental data and we estimated a few different parameters from that. First, we took a contact pressure estimation where we divided our critical load, so that's that experimentally measured critical load, divided by a projected contact area. So in all of these, our A is our contact radius, which we estimated from Hertzian contact. Certainly not perfect, but our first pass estimation. For our strain energy density, we took the total work, so that's that area under the load displacement curve, and divided it by a strained volume. So we estimated that as a spherical volume under the indenture tip, again, using that Hertzian contact radius. Right, and then lastly, we calculated a normalized thickness, which was just our Hertzian contact radius divided by our initial thickness. Before we did the test, we measured our thickness across all of our samples. So based on these data, we created contact pressure versus normalized thickness and strain energy density versus normalized thickness. And that allowed us to group our failure into 2 failure regimes using a machine learning approach. All right, so I'm going to jump into results on the microfracture study. Here is just our relaxation, reduced relaxation curve. So we've got relaxation degree on the vertical axis and time on the horizontal. So these are those stress relaxation curves starting just at the peak load. So the peak load has been normalized, but you can still see that the gag depleted relaxes more quickly than the intact samples. When we were looking at whether a specific loading rate was before the relaxations have occurred or after relaxations have occurred, we defined a transition regime that was between 50 and 90% relaxation. So we took 50 to 90% as our transition. We said less than 50%, we're going to consider pre-relaxed. That relaxation is happening very quickly there. More than 90%, we're going to consider relaxed. So for our gag depleted, what you see is our bounds there. So we're looking at a few seconds up to low teens as our transition time. And then for our intact, we have a wider transition where we're looking at 3 to 4 seconds up to about 18 seconds for our relaxation time. All right, so we'll end up using that then to say, where do these samples fall in terms of whether the samples are relaxed or not? To start off with on the experimental results for the microfracture, I'm just going to show two critical work plots, and then I'll jump more into the relaxation percentage and the failure regime clustering. So here we have the critical total work against the loading rate for our intact and our GAG depleted samples. There's a few things I want you to notice on here, right? So intact are the circular cyan marks. If we look at the furthest left, that's our fastest loading rate. That's our slowest loading rate. And then at the furthest right is our fastest loading rate. The GAG depleted then is our pink diamonds. On the furthest left and the furthest right, the two cases, the intact and the GAG depleted, have reasonable agreement in the critical total work. Whereas the transition is a little bit different between the two. And so that's going to map back to this idea of the relaxation times in those two sample types. When we looked at the effect of osmolarity, so here this plot now has the osmolarity on the horizontal axis. We just have those two extreme loading rates. The fast loading in green is that 5 millimeters per second. The slow loading in purple is the 5 microns per second. And here, the main thing that we saw with the osmolarity is that the osmolarity really only had an effect at the slow loading rate. Right? So those slow loading rates are, again, where we've got the case on the left on our first plot, where we have the greatest critical total work. So we can see that we can actually shift that total work by increasing our osmolarity. All right, so then jumping into our relaxation degree, this is now flipped from what we saw before. So here, can't see the label, the horizontal axis is critical time in seconds. Okay, and this is a log axis. So we've got, in this case, our fastest loading rate on the left. The samples that we loaded the fastest failed the fastest. They had the shortest critical time. And our slowest loading rates on the right, the samples that were loaded more slowly had a longer critical time. They took longer to fail. The shaded times in the middle are those transition times where, by our estimates, the things to the left of the shading, so this 1 point for the pink case and then the 2 points for the cyan case, are considered pre-relaxed. So in that case, we're saying 50% or less of the relaxation has occurred. And then over on the right, these are post-relaxed, so all of the poroelastic and viscoelastic relaxations have occurred. All right, so again, what I want to emphasize with this is that we do see these two apparent regimes, one where we've got most of the work, or arguably close to all of the work, just going into creating a new fracture surface. And that's what we're using to estimate toughness. And then on the far right, we have this idea that at the slower loading rate, we have poroelastic and viscoelastic relaxations that are increasing our total critical work. So what you would expect over on the right is that the sum of the total critical work is the work required to create a new fracture surface, and also the work that's been put into poroelastic and viscoelastic dissipations. So we use those data points that were on the left of the last plot then to estimate our fracture energy and work to fracture. And what you see here are the 3 dots from our experimental data. For the intact, which is the blue, we have 2 dots because we had 2 loading rates where we were in that pre-relaxed regime. And for the GAG depleted, we have just that 1 dot. And then this plot also gives you some comparison to kind of other common materials. So we've got a pretty tough material in cartilage, which has been described before. When we looked at our crack morphology, moving from the left to the right here, we're moving from the fastest loading rate, so pre-relaxed, over to the slowest loading rate. In the fastest loading rate case, we consistently saw these 2-branch or line-shaped cracks. So that was just the 2 branches. And then over to the right, we consistently saw the star-shaped or the 3-branch cracks. The other piece that I think raises some questions, and certainly be willing to have some discussion on this, if you look at the GAG depleted images, this middle, so the 0.5 millimeters per second for the GAG depleted, you can see that that crack has not fully closed up. We actually saw that in some percentage of our GAG depleted samples, which was kind of interesting. They didn't seem to recover as the other samples did. When we looked at our 2 failure regimes, we plotted the data from all of the studies together. So the intact and GAG depleted are the gray data. The different osmolarity are the purple and green data. Here we have contact pressure on the vertical versus normalized thickness on the horizontal. And from this data set, we ended up with two failure regimes, both for the contact pressure and for the strain energy density. Regime 1 is that kind of vertical regime where we have a relatively constant normalized thickness, but highly variable contact pressure and strain energy density. Whereas in regime 2, we have a relatively constant contact pressure and strain energy density, but a highly variable normalized thickness. All right, so I'll wrap up this first part of the study and then we'll jump into some metabolism work. So for the cartilage fracture, some of the key things that we've shown so far is that rate and matrix integrity both affect the crack nucleation. And we think this is through those poroelastic and viscoelastic relaxations. And then our toughness estimates, we do see they're similar magnitudes that are consistent with prior estimates. So we think that the method we're using to estimate this fracture toughness is reasonably reliable. One of the big questions certainly is, where does this go? I think we are still a ways from the clinical translation for a number of reasons, but the images that my clinical collaborator shares are still pretty motivating for the work that we're doing. So these arthroscopy images come from my colleague, Dr. Brian Walzak. And what I've asked him is, what do you do when you see a crack in the cartilage if you're in somebody's joint for an ACL repair, a meniscus repair, some other arthroscopy surgery, and you see a crack? And part of the answer is he doesn't fully know yet what to do. So one of the things he does is takes pretty images, but the direction that I definitely see this work going is coming back to this idea of when should we be concerned about a crack in cartilage? And what might we do? Is there some way to arrest a crack or provide some other intervention, especially if the surgeon is in there anyway? So longer term, that's the direction that I see this work going. Shorter term, we've got some other work to do. For the failure regimes, I propose these two failure regimes, one that's relatively strain governed, one that's relatively stress governed. And this might match with this ductile versus brittle. This idea has been suggested before, actually quite a while ago, so early 90s, where depending on the loading rate, you could consider cartilage failure as ductile versus brittle. The other thing that we think we're seeing in this is that there's some pressurization and fragmentation. So if we add our line versus star cracks on these two cases, our first case, our regime 1, is usually the line-shaped cracks, and our regime 2 is usually the star-shaped cracks. Those star-shaped, or those 3-branch cracks, may be consistent with this idea of a pressurization and a rupture. So this is this idea, if you think about inflating a balloon and then pricking it with a pin, if you have a heavily inflated balloon, it's gonna kind of burst, right? It's gonna create a lot of different fragments. And so one of the ideas that we're exploring with this is, are we creating a highly pressurized case with that slow loading rate that basically fragments in the same way that an overinflated balloon would? All right, so we'll hold questions for the end, but that's kind of the first half, the microfracture piece. For the second half of this talk, I want to circle back to those chondrocytes. And I said from a mechanics perspective, they're not doing a whole lot, and that's true. They're only 2 to 3% of the volume of the tissue in a mature animal, but they are there. And from what we've understood, in the last 10 to 15 years, they're not just passive remnants. They're actually capable of some activity. So with those chondrocytes, kind of the bigger picture question is, are those cells doing something in either accelerating osteoarthritis? So it could be that all of the work that they're doing is negative, or potentially fostering regeneration and repair. The approach that we're using to get at this is looking at metabolic byproducts, so autofluorescent byproducts of metabolism. Mechanical engineer perspective, right? So really high level, if we talk about cell metabolism, cells make energy. That's one of the things they do. It's not the only thing they do, but the two primary ways they make energy are through oxidative phosphorylation and glycolysis that happen in the mitochondria and the cytosol, respectively. We know that the mitochondria is the powerhouse of the cell, so that creates more ATP, but there's other reasons that cells shift between these. And some of that shift can be considered a redox imbalance, right? So if you have too much mitochondrial activity, that can create a little bit too much reactive oxygen species. This redox imbalance was classically described as a Warburg effect, in cancer, where you haven't, yes. The redox imbalance is traditionally a hallmark of cancer, where you see the Warburg effect. And the Warburg effect is a glycolytic phenotype where glycolysis is upregulated. So that's just one example, but this idea of a shift between these two ways of generating energy has definitely been described as either a hallmark or a driver of disease in the past. Now, we think cartilage is an interesting environment or an interesting case to kind of look at this idea of redox imbalance, in part because it has such a unique environment. In the mature animal, there are no blood vessels in the cartilage, so the oxygen concentration is relatively low, and people have estimated this as roughly 3 to 10%, so that's certainly below the 21% oxygen that most rooms are at. So this has meant that cartilage has a relatively high dependence on glycolysis for normal function, for energy production. However, the mitochondria have been shown to be present in chondrocyte, right? So they can see them, they can stain for them, and they seem to have some role in disease where reactive oxygen species and accumulation of reactive oxygen species has been described as a hallmark of OA, and the mitochondria can actually respond to mechanical load. So the way that we're putting all of this, or looking at all of this, is through a technique called optical redox imaging. So as I mentioned, we're looking at autofluorescent byproducts of metabolism. One of the byproducts that we look at is both NADH and NADPH together. They have the same excitation emission spectra, so it's both of those molecules. The other one that we look at is FAD, and that is a byproduct of oxidative phosphorylation. We are currently using an epifluorescent microscope, so the images actually project horribly on here. You can see generally in the FAD channel, you can see the cells. In the NADPH channel, you can see both the cells and some of the background. We've done a fair amount of work to confirm that our signal is not just governed by the background. So some comparison to 2-photon and some segmentation of the cells to be confident in what we're looking at. And we've also done some validation where we use channel-specific inhibitors and confirm that when we inhibit OXPHOS, we do in fact see a decrease in the FAD channel. When we inhibit glycolysis, we see a decrease in the NADPH channel. So there's 3 different pieces that we've looked at here. The first 2 are both mechanical loading. So we started off with this system. We validated that we were seeing something related to OXPHOS and something related to glycolysis. And then, of course, being mechanical engineers, knowing that cartilage is a heavily loaded tissue, we wanted to see what happens when we load the samples. So we have two different tips, really, is what we end up having here. Both of these setups sit on top of an inverted microscope, and they have this deformable backplate so that we can watch the cartilage sample while it is loaded, estimate the forces applied, calculate the bulk strain, and then we load it with 2 different platens. So on the left, what we have is just a flat platen. So this applies the load over the whole sample. And for those samples, we loaded them to 19% engineering strain at 5% per second, relatively slow loading. And that looks something like this, right? So we've got that compression across the whole sample. On the right, we have what looks in the cross section like a sphericonical indenter, but it's a rod attached to a triangle shape. Approximately the same engineering strain right under that indenter tip, so 18% strain, but at a much higher rate. And this video shows what that looks like. So the top in both of these, both the images on the left and the video on the right, is the articular surface. This particular sample is actually speckled for digital image correlation, so we weren't looking at the cells. But what you can see, if you watch very closely under that indenter tip, is some yielding, some actual fracture under the tip. So we know we've induced some pretty good damage there. The other piece that we've started to look at more recently is oxygen control. So we started out, I would say somewhat naively, looking at all of these experiments under room oxygen conditions, but I just told you that that's not what cartilage actually experiences in the body. So we built this test chamber where we've got nitrogen perfusion into the test chamber that basically pushes out the oxygen. We use an oxygen sensor then to confirm that we have dropped the oxygen in the test chamber. And for this, we looked at both the effects of oxygen and the effects of glucose, right? So the other key metabolic substrate in this OXPHOS and glycolysis setup. So we had our physoxia, that's kind of the purplish blues on the left, and then our hyperoxia. So physoxia is what we would expect cartilage to see in the body. Hyperoxia is what's actually room oxygen concentration. And then we did with and without glucose. And part of the glucose question is just recognizing that often when we broadly, the field, take cartilage samples and put them in media, we give them a ton of glucose, and that can very easily be messing with this balance as well. All right, so starting with our low level loading. So this is that compression across the whole sample surface. Here we have our NADPH channel on the left, our FAD channel on the right, and these are binned by time, right? So we applied our loading, and then we looked at different time bins after loading to see these responses. All of these data are normalized to baseline, to our measures before loading. And so what we saw in that low level loading was that our NADPH signal goes above 1 immediately after loading, but it comes back down to about 1 over those long time periods. But we didn't see any change, any response in the FAD channel. When we did this impact loading, or this higher level loading at a faster rate with a really sharp tip, we saw a response in both channels. So here, again, we have time on the horizontal axis. I am actually showing the baseline values here. So that's the BL is the pre-loading case. For both NADPH and FAD, we saw a decrease in the response after impact loading. So that makes sense. We expect that we're influencing those cells. Because we had this non-uniform strain field under the impact tip for this case, we also looked at the effect of distance from the impact. So we binned the experimental data where we've got our 0+ millimeters is right under the impact tip, and then we moved out to about 3 millimeters. This is a 6 millimeter diameter plug, so 3 millimeter radius. So the main thing that we saw here, which was unsurprising, but certainly gives us some directions to look in the future, is that right around the impact tip, where the samples saw the highest strains, most damage, was where we saw the greatest decrease in both the NADPH on the left and the FAD channel. All right, so the key takeaways here are that mechanical loading does affect these signals, and that there's a negative effect on both channels when we do what would be considered a traumatic loading, and a maybe small stimulatory effect on NADPH in a more physiological loading case. When we looked at oxygen and glucose availability, we actually only saw a response in the NADPH channel, which was kind of interesting. So here again, we have NADPH on the left, FAD on the right. These are an arbitrary units, so they're not normalized to baseline or anything like that. We saw that for our NADPH channel, there was a decrease in the hyperoxia case when you had, in comparison to the physoxia and the physoxia plus glucose. So some of this might have to do with the coupling between the different metabolic processes. All right, so key results from this optical redox imaging. As I said, the injurious loading affected both of the channels. We think that's potentially interesting as we move forward, as that could be a model system for damage that we could then try different interventions in. And then we also saw this influence of oxygen tension and glucose that influenced NADPH, but didn't have an effect on FAD. And this is a piece that we're certainly still working on interpreting. We would expect at some level that the oxygen availability should affect FAD. But as you recall with our loading case, we definitely saw that the FAD channel was a little bit slower to respond, seems to require a slightly larger perturbation. And this feature has actually also been shown in other cartilage behavior, where that glycolysis channel is a little bit more tunable, a little bit more reactive. We have some future work on here. What we're currently doing is coupling that mechanical loading with low oxygen. So we're building a device that puts it together so that we can impact load or physiologically load the samples at a physiological oxygen concentration. And then longer term, the vision that we have here is, again, if we go back to this case where a surgeon is in the joint doing some kind of arthroscopic surgery, can we build a tool based on optical redox imaging that actually helps that surgeon better diagnose what's going on with the cartilage, better understand what is the state of cartilage health, rather than necessarily just looking at it or maybe taking an MRI image that has a larger length scale. All right, so I'll wrap up there, right? The two different parts of the study, two different parts that I showed today. I'm definitely happy to answer questions on either. I will, of course, acknowledge the folks in the lab that did this work. So trainees Gubam Han, Dipal Chawla, Shannon Walsh, Josh Shelley, and Rick Sony. And my last plug for Madison, if you're looking for grad schools, I have some open positions. Thank you. Okay.
And then I'll do a little.
That's not sharing. Okay, great. And you can see it on there, but not on here. Is that right?
Yeah, so you're up.
Okay,
So we're
cool.
good.
All right.
So thank you very much, Professor Henak. And this is our upcoming seminar, December 2nd. Tyrone Porter from University of Texas at Austin, and talking on the diversity of lipid-coated nanoparticles in biomedical applications. And finally, with the next slide, just reminding everybody to check your Twitter accounts and stuff to stay up to date with Columbia BME. So with that, we'll take any questions from the live audience. At this point, I didn't see any on here, but anyway, it's good to start with the students or professors here. Yeah, Gerard.
And thank you. That was very nice. In the first part, is the first half, we're talking about the results. You had two regimes for the cracking and responsibility. And in the end, you were plotting them against the normalized things. So the rapid changes that you saw on the vertical axis occurred at the smaller normalized thicknesses, presumably when the emitter is small compared to the contact area is small compared to the thickness.
Right.
So those would be like less physiological, presumably because in a joint you have much more contact. Is that a correct interpretation?
Yeah, great. So I'm going to repeat the question just so the folks online can hear it. So the question was, in the first half of the study, in that regime 1, where we've got highly variable contact pressure and strain energy density, but a relatively low normalized thickness, which would then, as you said, correspond to a relatively low contact area. Is it true that that's not physiological? Is that a reasonable paraphrase?
Not asking if it's true, if it's not physiological. Is it correct to say that it's the slightly not less physiological?
Yes, yeah. So it is. Is it slightly less physiological? Yes. I mean, I would actually say, hopefully, in no case is a human in any of those contact areas, right? We have 100 micron tip. That's much smaller than the features that we have in the body. But the idea is that it can map out if we understand the toughness, if we kind of understand this overall paradigm where the energy can either go to recoverable dissipation or creating new surfaces. But yes, absolutely, we would have to scale up.
The reason I bring this up is because in the classical literature on impact injuries in cartilage, when the contact stress went above roughly 25 megapascal, the observation was that the cartilage would separate from the bone, the deep zone. So now it's like the whole thickness of the tissue is involved. So it becomes a little bit harder to compare this to the nano indentation, the tip results, which are focused very much on the surface. So I wanted to kind of get your perspective on that.
Yeah, great. So the literature that Gerard's bringing up is this kind of classical picture with you have impact across the whole joint. You can actually create delamination between the cartilage and the bone. He said that was about a 25 megapascal contact stress. Yeah, I mean, I guess I would say for me, the part of the motivation has been kind of this level of dissatisfaction in looking at a lot of the prior studies and the variability that's there. So I don't think we're there yet to the point where I can say like, well, here's what I measure in the lab. Here's the actual failure stress if you're going to create a surface fissure, or the actual failure stress if you're going to delaminate cartilage from the bone. And we can put that into a whole joint model and it's going to be accurate. But I think that's the direction that I want to build, rather than kind of this approach that others are taking, which again is definitely yielding results, but tends to be pretty study specific, where if you build the whole model, can you predict what the failure stresses would be in that specific setup for that specific set of constitutive assumptions and boundary and loading conditions, all of that kind of thing. To your question, can this tell us about delamination? No. I think delamination is an interesting failure type. I would say folks in the hip are also very interested in it, right? Because that's something that they see clinically in femoral acetabular impingement, is also a delamination of the cartilage of the bone, but certainly not something that we are currently touching at all. Yeah. There's a question over here.
Yeah, thanks so much for the talk. I have two questions that, feel free to interrupt me at any point. But so my first question is about this first study with the fracture lines that you're getting. My question was, for your example, were you tracking the split lines and seeing whether or not your fracture was helping like along the primary orientation of that, like all these or and were you getting different behavior when you had that kind of reverse this line versus the linear following if it going
Yes, that's a great question. So the question was on the microfracture, are those cracks following what's known as the split line? So in cartilage, if you prick it from the surface, it cracks along, creates a line, a crack that is aligned with the primary collagen orientation at the surface. We did not look at split lines. These are adolescent cartilage samples, so they don't have a fully developed extracellular matrix yet. With the microfracture, though, despite it not being physiological, that is part of our motivation in that we're not forcing the crack to go in a certain direction. Right? It can go in any direction it wants to go. We haven't looked real strictly at the collagen orientation at the surface. My best guess is for the lines, it's basically a split line test, right? For the line cracks. For the stars, it could be that it's a more random orientation that's allowing it to do that. I think, though, the fact that it's so governed by the loading rate tells us that there is something different going on. Fundamentally, I think if you've got that kind of crack, you're probably breaking collagen fibers at some level. From some of our earlier stuff, we did some SEM imaging that did actually show like you kind of have to break the collagen fibers to be at the tips. But we didn't repeat that for this study. So I think it is a very good question. Not one that we've addressed yet, though. So hopefully that gives at least some thoughts on it. Yeah, I don't see any other hands, so go for it. Yeah.
And the second question was kind of on the second study where you're looking at the behavior of chondrocytes and their reactions to I was wondering if you could look at the HIF1 alpha expression and look at either green knockdown or measuring the genome. I've seen it written, I've never expression because I think we have these markers of okay, this is where MSCs go into chondrocytes and so have this like I call it protective gene expression. I was wondering if you kind of share some of that with and the customer was looking into the
yeah, so the question is what molecular signaling, for example, for HIF1 alpha, have we been looking at? None. So, I will say like the optical redox imaging, we kind of started with, here's this interesting technique. Let's see what we can see. It's been a little bit more exploratory. We are definitely at a point where there's two different paths. Can we follow this road and see like what exactly are the mechanisms giving us these results? I think we more broadly can. I would say that's not my expertise. So the direction that we're going towards more is developing this as a tool. But certainly, I mean, there are a number of groups really following those pathways and trying to understand what's happening in chondrocytes that hopefully will be informative to our results, but is not the primary direction that we're going. But it definitely is a well-received comment because I think it's important. Yeah.
BJ?
Great talk. Again, I'm not an expert in cartilage or musculoskeletal, so it's coming maybe very new. So my understanding is in the first part, you talked about the back rolling on the cartilage. But if you look at osteoarthritis from a long-term perspective, it's primarily cognitive like cyclic wear and tear, maybe due to shear loading, right? Like rubbing against the tissue. So my question is, do you plan to use kind of like shear loading test to assess the failure? And secondly is, you also show the collagen structure, but I was confused if the collagen has some kind of like preferential orientation in tissue or like in arterial tissue, soft tissue, or is that going to be like along the road direction? Or is it very dispersed?
Yeah, okay, so the first question is osteoarthritis a failure, a wear and tear disease, or a traumatic loading disease? The answer is both. there's a lot of ways to get osteoarthritis. Traumatic loading is a nice paradigm to look at in the lab for two reasons. We can do it quickly, right? Like we don't have to repeat as many cycles. And of course, the cyclic loading becomes problematic when you're dealing with something that is so incredibly rate dependent. You can't, accelerating the cycles doesn't give you as realistic of a condition. So that's the first reason. The other is the traumatic loading is going to be what often causes early onset osteoarthritis. So these are athletes who have a traumatic injury. These are military population personnel. So those are the folks that can have some kind of traumatic injury earlier on in their 20s or 30s, need a joint replacement in their 50s or 60s. 60s is getting okay, but let's say 40s or 50s. And they're really earlier than you would ideally have a patient going in for a joint replacement. So there are multiple ways to get osteoarthritis. This impact injury paradigm is one that is pretty tractable and does actually have some clinical implication. Your second question was about the organization of the collagen fibers. So in the cross section that I showed, which was superficial zone, so articulating surface down to bone, the collagen fibers are mostly oriented with the surface, and then mostly random, and then mostly perpendicular to the bone. So they kind of have a, like this way all over the place and then perpendicular. And then if you're looking like at a joint surface from the surface down, they do have a preferred orientation. It's mostly in the direction of loading. And there is definitely a preferred orientation at the surface as well. So then I guess the other piece of the question that you asked is, are we going to do any shear loading? We are not currently. I think there's different schools of thought on whether to recapitulate the full joint, like you actually need shear and compression. As with the microfracture, I would say I believe firmly in this idea of well-controlled experimental settings, even if it's not the full physiological case, but that's what I would say is an ongoing discussion with grant reviewers and people like that.
So, yeah, I think we have one, Sean.
You mentioned that the potential application for the studies is in the future when you're in surgery and you're looking like what you do. Based on the findings that you have so far, what are some potential ways that the surgeon could pass fracture when they find it and you can just like.
Yeah, so the question was, what can a surgeon currently do when they have a fracture? I think the current surgical options are reasonably limited, right? They could debride it. They could try to clean it up if they're concerned that there's something that's maybe causing mechanical symptoms, catching and things like that. And there are groups working on injecting some kind of crosslink or other thing to stop a crack. Right now, if there's a relatively small crack in relatively healthy cartilage, the surgeon's probably not going to do much of anything. Because if they start removing it, then if they remove enough, they need to replace that with something else. So it has other complications there. I would say my vision for the future is there's a number of drugs. So for example, there's senolytics that are being pushed for intervention in cartilage disease. Ideally, if we understood how the chondrocytes were behaving, we could say more accurately for a given patient what class of drugs or what specific drugs or what type of dosing might be ideal for them. I do still think that's a ways off, but that's kind of one of the key directions. And then the other with this idea of like, how big is the crack and is it going to propagate, does need the parallel development of injectables or other techniques to cross-link or do a focal repair.
So maybe one last question.
See, the really interesting thought. Thank you so much. So you mentioned that you use like adolescent porcine explants.
Yep.
I'm kind of curious, like from my experience working with porcine explants, it's really hard to find them, even with potentially adolescent pigs that are not experiencing signs of so early OA. So I guess I'm curious, like how you tackle that, and whether you think like the age of your explants could like have an impact on your results.
All right, so this is a fascinating question. The question was, even with adolescent pigs, how often do they have osteoarthritis? Is that an issue? In our pigs, it hasn't been. And part of why I think this is fascinating is, so Wisconsin is the land grant university in Wisconsin. So we have a lot of a big ag school, part of which is the swine research and teaching unit. So one of the colleagues that I've been working with pretty closely runs the swine research and teaching unit. And like his whole world is understanding nutritional requirements, flooring requirements, this kind of thing to bring pigs up to speed for the meat industry. The pig is lame when it's 6 to 8 months, which is the kind of butcher age, can't walk off the truck, can't be eaten. So the industry is pretty motivated to avoid those things. So all of that is to say, in talking to him, it sounds like there is sufficient variability location to location based on flooring, based on things like our pigs having to jump up and down to get to their feed, somewhat based on nutrition. So like, depending on the mineral mix that they have or that kind of thing, can also be related to disease. So when they have a disease, if they have a certain disease outbreak, then those pigs can have developmentally different cartilage and bone, even if that disease is, then tamped down and those pigs are okay to go. So in our case, we have not seen any lesions actually that I can think of in that 6 to 6-ish month pig. We generally pull the patellas, but we have to open up the joint to see that the synovial fluid looks healthy, right? And the joint looks healthy. So my guess would be it's just going to be a plant variability thing, but I think that's an interesting thing to potentially be aware of. And pigs do develop osteoarthritis naturally, right? Which is again one of the reasons that we think they're a useful model, but at least in our hands, they don't have it yet at 6 months.
Help the rest of us. So let's then go. That's my next one.